Okay, so my talk, against the advice of the Simon's leadership, actually consists of two disconnected parts. So in the first part, I will talk about twisted tungsten diselenide, and I will tell about a new sort of an exotic sort of magnetism that we found in this system. And then the second part is motivated by the high TC materials, the Cuprates. And there in the second part, I will talk about the interplay between potential disorder and spin stripe order, and how this gives rise to a recently developed theory for strange metal behavior in these materials. But okay, first, twisted tungsten diselenide. So it has been discussed a few times already, also yesterday at the first part of the meeting, but I guess many people were not present there, so let me quickly review the experimental status. So this theory work that I will be talking about is motivated by the experiment that was as contained in this paper here. So there the authors, they took two layers of tungsten diselenide, they placed them on top of each other, and they used a twist angle between the two layers of 3.65 degrees. There's also other experiments, I think mainly by the Columbia group, on the same material but with a somewhat larger twist angle. So I won't be talking about modeling those experiments. I'm really only focusing on this one particular experiment where the twist angle was somewhat smaller. And this is believed to drive the system in a more strong coupling regime. And so here on the bottom of the slide, I'm showing the top two bands that you get from a continuum model that's supposed to describe this Moiré system. And so these are the two bands, the top two bands in one of the two valleys. And what's also important to keep in mind is that in this material, there's very strong Ising spin-orbit coupling, which means that the bands in one valley, in the K valley, they're spin polarized in the positive Z direction, and then the bands in the other valley, in the K prime valley, they are spin polarized along the negative Z direction. So electrons in valley K are spin up, electrons in valley K prime are spin down. And I will mostly be interested in a hole doping of one hole per Moiré unit cell. And that puts your Fermi energy right here, actually like in the figure, it puts it right in the middle of this top band here. And on the right here, this is a figure of a cartoon of the experimental device. So here is the twisted tungsten diselenide, and then there's some dielectric environment, and then there's a top graphite gate, a bottom graphite gate. And so with this dual gated device, the experimentalists can apply a displacement field, so an electrical field perpendicular to the tungsten diselenide planes. And so these are two plots from this experimental paper. So they're color plots showing us the resistivity at two different temperatures. And so along the x-axis, you see the hole filling. And so this is the hole filling that I'm most interested in. So the hole filling of one hole per Moiré unit cell. And the y-axis here is this displacement fields. And what you see at a temperature of 10 Kelvin, you see a high resistance region emerge here, starting at hole filling 1. And as you cool to 50 millikelvins, you see that at this hole filling of 1, there's two high resistance regions, so two insulating regions, and then a low resistance region here around zero displacement fields. And as you zoom in on that region, you see it's really a zero resistance region, and there's really superconductivity there. So, okay, this is not a high TC. The TC is higher than 50 millikelvin, but it's not very high. But I think the reason why this is interesting and why we should be thinking about this is that this is a system where clearly the Coulomb interaction is not a bystander. The Coulomb interaction is really in the driver's seat here, and it's really determining the key physics that's taking place. And so we have here a system where, as you change the displacement field, it goes from being an insulator to being a superconductor at the same filling. And I think that's very intriguing. And it's really worth thinking about and trying to understand this. Okay, so these are the experimental results. I will just start by telling what we found. What we found theoretically for this system. So what we did is we did the thing you would do first. So self-consistent. We did self-consistent mean field study, and the upshot is that we found this very exotic type of magnetism in the system. And what I will first describe the sort of magnetism we found, and then later on I will situate it in the phase diagram. So I will tell you where exactly we found this type of magnetism. Okay, good. So first, what does it look like? So here on the top left plot, what I'm showing here is the in-plane magnetic moment as a function of the spatial coordinate, basically. So this is a real space plot. And so these red blobs, they are basically, they represent the size of the in-plane moment, and the black arrows represent the direction of the in-plane moments. And so this is on the top tungsten diselenide layer here, and then this is the bottom tungsten diselenide layer. And so this state, if you look at the top layer, you clearly see this triangular lattice, and that's the Moiré superlattice. And you also see that this in-plane magnetic moment makes this familiar 120-degree antiferromagnetic state on this triangular lattice. And so this state, this is not the unconventional state that I'm talking about, or that I have been referring to. And this state has already been had been found before in other studies, other theoretical studies in this system. But the state we find actually is this one. And what you see here is a more complex pattern. It has a larger spatial unit cell. And what's happening is that in 1/4 of the Moiré unit cells, you see that the magnitude of the in-plane magnetic moment decreases a lot, and it's actually replaced by a significant out-of-plane moment. And so what happens is that we have this this triangular lattice of out-of-plane ferromagnetism, which is interwoven with this remaining Kagome lattice, where the moments still form this 120-degree order, but now on this Kagome lattice. And so this is the type of magnetism. This is the new type of magnetism that I'm talking about. It's a multi-Q order because this magnetic texture, it varies in space with 4 different non-zero wave vectors. One being the K point of the Moiré Brillouin zone, and the 3 others being the M points of the Moiré Brillouin zone. Okay, so this is the magnetism we found. Now, where did we find it? What we did is we did a 2-dimensional parameter scan. So the interaction we added to the system, to the continuum model, was this gate-screened Coulomb interaction. The potential there and momentum space is written on the top of the slide. So D is the gate sample gate distance, and what we varied is the dielectric constant epsilon. So that's what's shown here on the x-axis. So going to the right, the bigger dielectric constant is weaker interactions, and then the y-axis is the other parameter we varied, which is this displacement field. And on the top left plot here, this is I named it the IVC order parameter. But because of the spin valley locking, this is really the in-plane magnetic moment, the size of the in-plane magnetic moment. And you see there's a large region where this is non-zero, almost everywhere in the phase diagram. The top right figure here, I'm showing a time reversal breaking order parameter, but this is a special, it's not the Kramer's time reversal, it's a different type of time reversal, which only flips the out-of-plane components of the spins. And so in most of the phase diagram, this order parameter is actually 0, which means that this symmetry is not broken. And it's actually, this symmetry is not broken where you actually have purely in-plane spin order. So this 120-degree state actually preserves this symmetry. And then the bottom left, this is an order parameter for also an unconventional type of translation symmetry. So this is a translation symmetry where you translate your lattice, and then you rotate the spins by 120 degrees. And this is, again, a symmetry of the 120-degree AFM, so the order parameter is 0 here. And this is then the mean field band gap, and this is just to show that almost everywhere where we have magnetism, so where we have a non-zero order parameter, there is a band gap, or at least at mean field level. Okay, so here, this is, like I said, the 120-degree state, right? It has in-plane magnetism, no out-of-plane magnetism, and it's invariant under translating and rotating spins along the z-axis by 120 degrees. But then here we see this other region appear where actually this modified translation symmetry is broken, and it also, in a part of phase diagram, actually breaks this time reversal symmetry, so it actually also has a part of, in the part of the region, this in a part of the phase diagram, we also get a translation symmetry breaking state, which has an out-of-plane magnetic moment. And so these are the multi-Q orders that I was talking about. So we find them at somewhat, at moderate values of the dielectric constant, and for around basically 0 displacement field. The reason I'm talking about magnetism at basically collaboration about superconductivity is that I believe there's a very strong connection between this magnetism or the magnetic fluctuations and the superconductivity. And the reason that I believe there's such a connection is that if we start in this 120-degree AFM, and as we approach this multi-Q state, this multi-Q magnetism, we see that it's accompanied by continuous softening of the spin fluctuations at the endpoints. So what I'm plotting here is, this is a cut through the mini-Brillouin zone or through the Moiré-Brillouin zone, basically along the x-axis, so it cuts through the gamma point and this endpoint here. And you see here, this is the spectrum of the spin fluctuations of the magnons, basically. And you indeed see that at the endpoint, as I approach this transition here, there's a softening of the spin fluctuations at the endpoint. And then similarly, so this is at fixed displacement field, increasing dielectric constant. And then similarly, if you work at a fixed dielectric constant, but lower the displacement field and approach the transition from here, you also see this lowering of the energy of the spin fluctuations at the endpoints. So I'm only showing the behavior here at the M1 point, but we always find that the threefold rotation symmetry is retained, so we have the same behavior at the M2 and the M3 points. So this is just to say that this transition seems to be continuous. And so we see this condensation here of this bosonic mode at the endpoints, which are indeed the ordering wave vectors of the static multi-Q order that I was showing previously. To be honest, we haven't looked into that, what the polarization is.
The direction of the spin?
Well, you would think, okay, so, oh, you mean the spin, okay, the spin polarization. Okay, I think since they develop an out-of-plane component, I would think they are out of plane. There's some out-of-plane, yeah. I'm not completely sure, but I think that's the case. Mm-hmm.
How is this related to the superconductivity experiment?
Right. No, I'm getting to that. Yes. So far, I've only been talking about magnetism. I'm building up to the connection to superconductivity, which I must confess we haven't really worked that out. But the reason I'm talking about this is that I think what's going on is actually, I don't think this multi-Q order is actually present as a static order in the system. I don't think that's really happening. I don't think they see this order in the experiment. But I really think these low energy spin fluctuations are there. So this multi-Q order is there as a fluctuating order. And one indication is that you can actually estimate what the correct value is for this dielectric constant that you should use by comparing the layer polarized regime, so you can apply a displacement field and then look in your Hartree-Fock or your self-consistent mean field, when do the electrons basically polarize to one of the two layers, tungsten-selenide layers. And you can do this for different values of the interaction. And you find that if you, in the mean fields calculations, you use this dielectric constant of 30, then you find the layer polarized regime at roughly the same displacement field as in the experiment. So that seems to be a good indication that, well, you should use this dielectric constant of 30. And for that value, actually, okay, so with that value, we're actually here, okay, we're somewhat close to the boundary of this phase transition, this mean field phase transition. Now, given that fluctuations beyond mean fields likely push this transition to higher epsilon, so it probably pushes it to somewhere here. So I think we're actually pretty close to where the actual phase transition could be. And so where we could actually have really low energy spin fluctuation at the endpoints. Another reason that I'm pretty convinced that these modes are there is that I think they've actually been seen in experiments. There has been a recent pump probe experiment looking at collective modes. And they saw clear evidence for a fast collective, neutral collective mode, and a slow neutral collective mode. So the fast mode was interpreted by the experimentalists as the Goldstone mode, the spin wave of this AFM. And I think that's pretty clear. I think that's a pretty convincing interpretation. But then they interpreted the slow mode as the amplitude mode. I think actually from these calculations, I would actually suggest that the slow mode they saw is actually, are actually these endpoint fluctuations. And definitely in our calculations, the energy of these endpoint fluctuations, the mass of these fluctuations, is like at least an order of magnitude smaller than the mass of the amplitude mode. So, so I think actually what they saw in this paper, this experiment, I think they actually saw these endpoint fluctuations. And of course, now we have these low energy spin fluctuations. There's of course an old story. Spin fluctuations are probably one of the most discussed alternatives for phonal mediated pairing. And so now this happens, I think, in a system of which we have, like, not we, but the experimentalists have very good control. So I think we should now investigate this scenario. And I'm actually pretty positive that we can, well, develop more insight in spin fluctuation mediated pairing in the system. So, but okay, that's hopefully something I will be able to talk about at next year's meeting. Okay. Any other questions about the first part? No? Okay. So then I will switch to the second part of my talk, so which is about potential disorder and spin stripes. So as I said at the beginning of my talk, this is motivated by thinking about the cuprates. And so it's well documented that in the underdoped region of the cuprates, there's various forms of static or fluctuating stripe orders. So basically unidirectional charge density wave orders or spin density wave orders. And for example, you can read these two reviews to learn about that. And so here I will be thinking about these spin stripe orders. And in their most simplest form, you can describe them with the following order parameter. So if you just calculate the local expectation value of the spin, and you isolate this fast oscillating antiferromagnetic sign factor here, then what remains in these spin stripes, in the simplest spin stripes, is just a single cosine, so a single standing wave. And so what you get is you get a magnetic pattern where if you plot this is the direction of the Niel order, right? Then it has these one-dimensional extended regions where it's basically non-zero. And then this in between those regions, the antiferromagnetic order goes to 0. And whenever you cross these gray lines, which is where there is no antiferromagnetic order, whenever you cross one of those lines, the direction actually changes of the Niel order. So you have up, down, up, etc. And so it's also known that whenever you have this sort of spin density wave order, there's also unavoidably a charge density wave order associated with it. And in particular, what you find is that along these gray lines here, so where the antiferrometric order or the Néel order goes to 0, that's where actually you accumulate charge. And in particular, in the context of the Cuprates, this is where you accumulate actually holes. So you actually get a dip. You get a dip in the charge density whenever you cross, cross these two regions with antiferrometric order. Okay, and so in the rest of my talk, I will be working with this Fourier component here, this order, SQ. And in particular, I will decompose it in its real and imaginary parts. So phi1 and phi2, they are the real and imaginary parts of this Fourier component of the order. And I will just, from now on, always work with this phi, which is now a 2×3 real matrix field. And that's my order parameter field that I will be using. And I will use it to write down a Lambda-Ginsburg action for the spin stripe order. It has a lot of terms, but actually you know most of them. The first term is these first terms here are standard temporal and spatial stiffness terms for the order parameter field phi. The terms in the last line, on the last line here, they are, the first two are just the standard Mexican head potential terms. And then this other quartic term, this is a term which ensures that phi indeed describes spin density wave order. Because this field could also describe, for example, spin spiral order that would have the same type of order parameter fields. But this quartic term here ensures that phi indeed realizes a spin density wave state. Okay, so this is just a field potential term, this last line. And then what remains is the middle line here, these two terms. And they're again temporal and spatial stiffness terms, but now not for phi, not for our original field, but for this composite field phi times phi transpose. So this is sometimes this composite field also goes under the name sometimes of a vestigial order parameter. It's an order parameter for vestigial order. And it's an order parameter which basically these two terms, they're insensitive to basically the phase-on fluctuations of your charge density wave order. So they're insensitive to charge fluctuations, but they raise the action. They are sensitive to fluctuations in the spins. So basically this term here, this J, is a stiffness for both charge and spin fluctuations. This J tilde here is a stiffness only for spin fluctuations. And so by adding the J tilde term, I'm making the spin fluctuations stiffer than the charge fluctuations. Okay. And I will now be using this theory with a fixed non-zero J tilde and a fixed field potential, and then vary the stiffness J here. And this realizes this phase diagram. So the y-axis is the temperature, and then the x-axis is 1 over the stiffness. So going to the right is actually lowering the stiffness for order parameter fluctuations. And so focusing first on zero temperature, at large stiffness, we start in the spin density wave state, or equivalently, this is the spin stripe. Then as you decrease the stiffness, first the charge degrees of freedom disorder. But when this happens, you actually don't go to a completely symmetric state. You actually go to what is called a spin-nematic state. That's because what's going on is really, if you look at this picture, charge fluctuations, so the phase-on fluctuations, you should imagine that these domain walls here, these gray lines, they start fluctuating. And so whenever this gray line passes through the spins, through the antiferrometric order, they change direction. So when these gray lines, the charge order starts fluctuating, the direction of the spins unavoidably also starts fluctuating. So the magnetism is gone, because the direction of the spins will be disordered. But the spins do remember that there is a fixed axis in the system. So there is a preferred axis, but still there's no magnetism, and that's, of course, those are the properties of a spin-nematic order. So by first disordering the charge degrees of freedom, or the phase-on of the charge density wave order, you go from the spin stripe to the spin-nematic. And as you then further decrease the stiffness, also the system also forgets about the fixed axis, and you go to a completely completely symmetric state. And so these two phase transitions are in the O2 universality class if you assume an incommensurate charge density wave, and the O3 universality class. And as you raise the temperature, as this is a 2D system, the magnetism goes away at any finite temperature, and the spin stripe becomes a charge density wave. If it's incommensurate at higher temperature, it will go away via BKT transition. And then here the spin nematic order disappears at any non-zero temperature. And then this dashed line is a crossover region, which is the onset of local spin nematic order. So that's the clean phase diagram. That's not a new result. Yeah.
Shouldn't there be an Ising-like transition as temperature into the nematic phase?
Ising, oh, sorry, where?
They have spin orbit coupling.
Sorry?
There's no spin orbit coupling. So it's
Okay, but this type of physics was known, I mean, this is known for a long time, that's basically fluctuating. The main point here is that fluctuating spin type order can give you spin nematic order. Okay, but now I want to take this phase diagram and add on top of this conventional doping-induced potential disorder. Okay, what will happen? First, actually, let me go back. The main thing I want to discuss is what happens to the spin nematic as you now add basically potential disorder. Well, the correct way to think about the spin nematic is that it's really a disordered spin stripes. It's really disordered by charge fluctuations. And so once you quench the charge fluctuations with a random potential, and so you you really pin a particular inhomogeneous charge distribution, the spin nematic will then pin, the magnetism should come back, and you will pin a magnetic order to this charge configuration. So really, because what made the magnetism go away was charge fluctuations. So if you quench the charge fluctuations with a random potential, the magnetism should also come back. And that's really what happens. Well, if the disorder is not too small, at least. One important caveat is that the disorder actually can induce, so charge disorder, definitely short-range charge disorder, actually induces frustration for spin order. And the reason is that if you have in a random configuration, you can have these dislocations, so where one of these gray lines just ends. This is a dislocation in the charge density wave order. So then the spins are frustrated. They don't really know what to do, because when they cross such a line, they should change their direction. But you can so go from here to here by either not crossing such a line or by crossing such a line. So there's kind of an ambiguity on how you should order, or how you should pin the spin, or how you should pin the spin order to this charge order. Of course, if you have a double dislocation, then there's no problem. It's really only the single dislocations which introduce frustration into the problem. Yeah. So and the
nematic phase is shown here as something which has a direction, and it has topological defects.
no, this is actually this is the spin stripe order really.
But this is at 0 temperature, or this is something which occurs only at constant.
This would be at 0 temperature, yes. Yeah.
Very good.
Yeah.
Okay, because I was worried about what happens to magnetic order at non-zero.
Disorder, yeah, of course, the disorders, yeah. Okay, so what does this, basically this type of frustration, it manifests itself in the Landau-Ginzburg theory by basically that if you keep the low energy configurations of your field, you basically find out that part of your system reduces to an Ising spin glass Hamiltonian. So actually you find that these type of dislocations actually give rise to glassy Ising, glassy physics for the spins. Okay, and so this is then the phase diagram you have with disorder. So here for reference on the top right is again the clean phase diagram. And actually, let me ignore the left possibility. This is what happens with weaker disorder, but actually that's not important for the rest of my story. Let's just focus on this phase diagram here. It actually seemingly becomes a lot simpler, because now the spin nematic becomes what is called the spin density wave glass, right? This is this Ising glassy order now, and with this random charge configuration with a frustrated spin order pinned to it. So this is called the spin density wave glass. And then there's a single O3 transition that remains from the pure model that separates the spin density wave glass from a state where the magnetism is gone.
Why is it Ising? Is it a Heisenberg class?
No, it's Ising. And the reason is that, if you go back, so actually what it will do is, if the spin stiffness is large enough, you actually don't want to introduce vortices where you start twisting the spin configuration. Because you have a large core energy and a large elastic energy to do that. So you kind of want to keep a fixed direction for the spins. It turns out the cheapest way to relieve the frustration is by introducing a small Ising domain wall here. So basically you get a configuration of Ising domain walls in this system. And that's where you get the Ising physics from. It's really because this gray line, this hole rich region, acts as an Ising domain wall. The spins flip direction across this domain wall. So it's really what is disordered is purely Z2 Ising degree of freedom, because there's a fixed axis. Because it's still spin nematic. The system has a fixed axis. And the degree of freedom is really choosing a direction along this axis. And that's the Ising degree of freedom. Okay, right. And so this is basically all that remains when you add now potential disorder to the system. So the spin nematic becomes a spin density wave glass. It turns out also the spin stripe actually becomes the same phase of matter. There's no phase transition here anymore. Also, Imri-Ma tells us that, well, Imri-Ma basically tells us that the charge order here also disappears. This is why also there's no phase transition anymore. So basically that's why, well, this phase transition goes away, then the BKT goes away. These are now all crossover regions, and this all becomes the spin density wave glass. And there's a single quantum phase transition that remains, which is this O3 transition. But this is now an O3 transition in a completely different universality class than this transition. Basically because this transition is basically standard Wilson-Fisher, because the Fermi surface reconstruction here happens if you couple it to fermions. So you haven't mentioned that. If you couple this order parameter to fermions, there will be Fermi surface reconstruction at the O2 transition. But then the spin nematic order parameter has no Yukawa coupling to the fermions. So this is actually, even in the presence of a Fermi surface, this O3 transition is basically still Wilson-Fisher. But now with disorder, that's no longer true. And this O3 transition belongs now to a different universality class. And so if you just take your Landau-Ginzburg theory, you couple it to fermions, so you promote your Landau-Ginzburg theory to a Landau-Ginzburg-Hertz-Millis theory. Then if you take that theory and you put in the disorder, and you can derive by a few simple steps what is now the effective theory for this O3 transition. You find it's of this form, and it's very simple, well, deceptively simple. There's a free fermion term, so there's some potential disorder for the fermions. Then there's this critical, this field here which describes the spin fluctuations. This is the field which becomes critical here at the O3 transition. And then there's a Yukawa coupling between the two. But importantly, the coupling constant now depends, it varies from point to point. And it actually takes on this form. So before we started out with a Landau-Ginzburg-Hertz-Millis theory with a constant G, but now, so that's this constant G from the really UV theory. But now the effective GR is this constant, this coupling constant, times SR. This is basically the Ising spin degree of freedom. And then there's some cosine. This doesn't matter. This is some other, comes from the disorder as well. But the important thing is this degree of freedom here. This is the Ising degree of freedom. And this Ising degree of freedom is basically in a random Ising spin glass configuration. So you get really now a coupling constant which varies randomly from point to point. And importantly, its average is 0. There's no homogeneous component to this coupling constant anymore. It's really, it fluctuates around, well, it has a 0 mean, basically. And so this is exactly the theory that's attracted a lot of attention in the last few years. And it was shown and argued in a series of papers. There's many more. My apologies well, there's people here who have worked on this, and I'm not citing them, but I just try to, well, I only have 3 citations, but there's many more. And all these works showed basically, or argued, that this theory at the critical point for the boson has linear T resistivity, marginal Fermi liquid behavior, so it has all the right properties to describe the strange metal in the cuprates. So there's lots of large N studies, just like Yukawa, SYK type of physics. But then there's also this very impressive numerical work, this QMC work basically, which didn't rely on a large N limit. And they also found linear T resistivity in this model. And all these models, they argue that it's crucial to get this randomness here in the coupling between the boson and the fermions. And also what's actually quite nice is that it was also shown that if you want to get a Planckian scattering rate, which is found in some cuprates, then you really need this G, the homogeneous part of this G to be very small. And here we're in the ideal situation because there's no homogeneous parts. This GR is completely random with 0 mean. So that seems to be the ideal case for getting a Planckian scattering rate. Okay. All right, so that's the main, that was the main takeaway message of the second part of my talk. So the only thing that remains is to thank my collaborators. So Arthur is a PhD student, Nai Chao is here, he's a postdoc in Ghent, and then Xu is another postdoc in Ghent. So, so thank you.
Thank you very much. Okay. More questions? There were many during the talk, but... Okay, yes.
So just to make sure I understand, so the isinglass phase, if we look at the local expectation value of the spin, that's going to be non-zero, but all polarized in one direction. There's not going to be any tilted spins anywhere.
Well, I think there can be slight variation, but I think generally is that I think that's at least the simplest version of the theory. That's what it would say. Yes, it would just have.
It just seems hard to rotate a little, and then you have all sorts of new modes. It really is a different symmetry state. Right?
Yes, I agree. And so actually, so this. So this paper here, in the numerics, what they actually found is that if you take, basically because of the RKKY interaction with the fermions and this random coupling, you can actually also, you can generate type of Heisenberg type of spin glass physics. So definitely the fermions want to twist the spins away. Yeah. But that actually has not been taken into account here. If you purely look at the bosonic part of the action, there's no term that would really want to do that. No, the disorder doesn't do that.
Andre.
I had a quick question about the first part. So, just as a caveat, so Dimitri also found this endpoint phase that you're talking about, but I thought it's in a very narrow region of epsilon and doesn't start from u equals to 0, displacement u equals to 0. So, whereas superconductivity there, right? It's in the experiment. Everywhere around displacement field 0 until you get to infinity, right?
Right. Right. So what I
How do you, is it published? Or?
yes, it's published. Actually, I wasn't aware of this.
Oh, we didn't publish it.
Ah, okay, because we did to make sure that this statement is sufficiently general. We used two different continuum models. The most commonly used one, which was introduced by Alan, the lowest order model. But we also used your higher order model with higher gradient terms and higher harmonics. And in both models, we find this order. And in both models, it's actually strongest at exactly 0 displacement field. We do find it at 0 displacement field.
Well, maybe you should talk about it.
Yeah.
The space diagram shows a little bit above.
Okay, well, yeah, I think.
Maybe you can comment.
Yeah. I mean, we see it in a very narrow region of the phase diagrams.
Mm-hmm.
Well, narrow tuition.
Okay, yeah, okay.
Okay, Steve.
And actually, well, let me first comment on what do I think is going on. Well, so the multi-Q order is much weaker than the 120-degree AFM. And I think what's happening here, this high resistance region, as you heat up the system, the multi-Q order would no longer be an instability, even at mean field level. And what you find is that if you suppress by hand the multi-Q order, the system actually at 0 temperature doesn't become metallic. So I think what's pretty reasonable is that as you heat up the system, and there's no longer an instability to the multi-Q order, you actually find a 120-degree antiferromagnetic metal. And then that could serve as an apparent state as you then cool it down instead of really having these modes condense and forming static order, which actually the order actually preempted by superconductivity. And it's exactly in this region where we have these low energy spin fluctuations. But you see, as you heat it up, I think this is a strong piece of evidence. As you heat up the system, this becomes basically a featureless blob, which seems to be just nothing going on here and there. So, yeah.
Steve still had a question.
Okay. There are not lots of other pressing questions. So imagine a rare event where you have a line of dislocations.
Mm-hmm. Yeah.
So then if you had an Ising, it would cost linearly.
Yeah, you want to make a vortex. Yes.
So I think there will be at least some place.
Oh, I see. You're worried. Okay. Now I understand. Yes. You're absolutely right. Okay. Let me go back to my cartoon picture. So. Yes, one way to relieve the frustrations is introduce also a singularity. Well, also let the spins basically make a vortex and let them twist as you go around the singularity, right? Yeah. Then you make, well, basically the equivalent of a half vortex for the paradensity wave state, which was introduced, well, by people here in the audience. This is the equivalent of the half vortex, but for the spin stripe, right? Yes. So that. But then, of course, yeah, you pay some. There's going to be some logarithmic elastic energy associated with that. But indeed, if you have two dislocations close enough to each other, that could be rare regions where this happens. Yes. But as long as you have pairs of vortices and they don't proliferate, I think at long distances it's still Ising spin glass.
I'm not sure, but I mean, it means that there is a breaking also of rotation symmetry about the local program.
Yes.
About
Yes.
the Ising axis.
Yes. And I agree. Actually, we cannot rule it out completely. But I think the main point is that even if that were to happen, and what's actually another possibility is that if you have very slowly varying disorder, there's actually almost no dislocations at all. That could also be a possibility. But actually, none of that really matters. You would still have basically the same theory. But now, just that this S would not be an Ising spin glass, but could now be more general. It doesn't really change the main message of the story. Yeah.
Yeah, Anton?
Yeah, I think that works. So if I have a finite average value of G, right, that's bad for strange metal, correct?
Well, definitely I think definitely in these original papers they claim that, of course, there will be some energy scale that will become smaller, but right. I think they find linear T resistivity for a small fluctuating component. That would be perturbation on top of a homogeneous part. Okay. But it would be bad for Planck.
Really, my question is, how come average value of G became 0? Because the dominant coupling are still antiferromagnetic. N is the sigma model vector for the Néel order, right?
Yeah.
So how did you argue that G has 0 average?
Oh, it never actually, okay. It's a very bimodal distribution. It's actually never zero. It's just like plus minus. It's like, well, an Edwards-Anderson type of plus minus, plus minus.
It has zero average.
Yeah.
Why?
Oh, because the S, this Ising, this is the Ising spin degree of freedom, and this in the glassy order is just it's going to be randomly up or down as a function of position. There's no long-range order. There's no long-range ferromagnetic order in this Ising degree of freedom. That's all you need, and it can be Ising spin glass. Even if there's no dislocations, it will be an unfrustrated system, but still it will have random directions. Yeah. You never. I don't think you ever have long-range ferromagnetic order in this.
Anti-ferromagnetic. You're talking about the.
So yeah, this is the antiferromagnetic component here. Sorry, yes, you're right. I always strip it off and make the antiferromagnetic to ferromagnet. Yes.
All right, I don't see any more questions, so let's thank Nick again.